All right, so polarization of sunlight, that can be a bit confusing. I don't have a good explanation for why it's plane polarized after the reflection. I try to think of the vectors of the electric field and how they're transmitted through the new medium, and how basically matching that angle up somehow takes those components away, since it's being all transmitted versus reflected. Not exactly sure, it's just an idea I have in my head, but you should just try to look at it and come up with your own explanations. Well, look it up. I haven't been able to find one in any of my textbooks or online that's been satisfactory. So anyways, let's talk about polarizers through, let's talk about polarizers, okay? Polarization in this sense makes a lot, is much more sensible to understand, okay? One other thing actually from the last notes, I think in the notes we had it as phi, you can change that with the theta sub I there, all right? That's not too hard. Anyways, polarizer, all right, it's going to be a device that produces plane polarized light from an unpolarized beam. So what this effectively means is that if we have completely random light coming in, okay, we're going to cause the unpolarized light coming in, okay, electric fields going in every direction. Polarizer is going to restrict that to only one direction, okay? So the transmission axis is this direction of polarization, all right? That's allowed by polarizer. Okay, so the way I always think about this is if we took, if we had like a big, wooden panel here, and we cut a, hole like this through it, all right? Took a rope, and we're shaking that rope up and down through it, okay? That rope would be allowed to travel, those waves would be allowed to travel through here as long as those waves we're making are in the same direction as the hole. But as soon as you change that direction of the hole, okay, the waves that we'd be making up and down over here would not be allowed through this little wooden block anymore. Right? That's effectively the way a polarizer works, okay? It's only going to let waves through that vibrate in the direction in which it has those openings, all right? So if we take a look here, okay, in your packet there, there's one thing I would like to note as well before we move on, sorry. Please note that polarization only works for one type of wave. Transverse waves are the only waves that can be polarized. Longitudinal waves, like sound waves, cannot be polarized. Okay. All right. So moving on here. We have unpolarized light, okay, coming through a polarizer. This middle guy is the polarizer. Okay. Its transmission axis is this vertical axis, so it's only going to let light through with electric fields that are vibrating in that direction. Okay. Not only that, but it's only going to allow the components of every other wave of light that are vertical through. So it's actually a vector component problem. So if we have truly random electric fields vibrating in all directions, okay, then half of those components, vector components, must be vertical, and the other half must be horizontal. So what we actually see here, okay, we have the unpolarized light intensity is I naught. You can go ahead and write that down, all right? What ends up happening is that after unpolarized light is incident on a polarizer, okay, the polarized light intensity ends up being half the intensity of the original light. And the reason is it's only letting through the vertical components. There's exactly half the components are vertical and half the components are horizontal. Okay? So that's the Y. Okay? Half vector components horizontal and half are vertical. All right? So they're having one direction or another, and that's why we end up with that. So that's the way a polarizer works for light. Okay, so really quickly, okay, glare, a couple things to define here, right? Is mostly horizontally polarized light. Okay, this is getting at that reflection of light, okay, off of a non-metallic surface. Okay, because off of a metallic surface, it doesn't polarize, all right? So sunglasses have vertical transmission axes, okay, and it only lets in vertically polarized light. So sunglasses, therefore, okay, end up blocking out glare. If you have a pair of polarized sunglasses, there's some pretty cool things that you can do with them. If you have a couple pairs, you can actually block out all light if you hold them perpendicular to each other. And there's also some cool things. You can see the stresses in different plastics, especially with rear windshields and whatnot. You can actually see where the windshield is stressed. We're going to talk about this in a little bit here. Okay, so all right, you can answer all those questions there. Okay, how sunglasses work. You have that cool diagram with that guy who looks like he has on those futuristic glasses, but it's just an exaggerated diagram of polarized sunglasses. All right. So we have this new, we have a little idea here we're going to define what an analyzer is. Okay, an analyzer, right, is a polarizer that's used to detect polarized light. Okay, so before we're talking about using polarizers to make light polarized, okay, used to detect. Now we have polarizers that can detect polarized light as well, if we use them a certain way. So the way that we use an analyzer, all right, is that if we have unpolarized light coming through, and we don't know what direction this first polarizer polarizes it, we'll say, okay, we place our analyzer in a certain direction, all right? What we do is we measure the intensity of the light that comes through here. If we get the same intensity of light coming through, we know that the analyzer is in the same direction as the previous polarizer, okay? If we get absolutely no light coming through, we know the analyzer is at a right angle to the initial polarizer, okay? So that's the idea of an analyzer right there, to help us tell what direction the polarized light has been put in. And the reason for this is that we sometimes don't know which way a polarizer is going to polarize light, and we need to be able to detect that, all right? So how do we calculate this? How do we actually know this, all right? So what ends up happening, okay, is the component, okay, again, if it's not perpendicular or parallel, we need to actually calculate some things here. So the component of the light parallel to the transmission axis of the analyzer is allowed to pass through. Actually, okay? So what this is saying is kind of like before what I said, you know, we've got to consider that these waves have components in different directions, and that actually that energy does get through, okay? So if the first polarizer polarizes it in this direction, okay, and our next polarizer is at this angle, then what we got to do is consider this component of this little right triangle, okay, the one that's parallel. So actually I'm going to redraw this really quickly, make this guy black here, okay, and this guy in blue. So the parallel component here is my red one, all right. This is probably my blue one. The blue is a parallel in the same direction as before, all right? And actually, excuse me, no, I take that back. There we go, sorry. This guy right here, this right there, it's just, sorry, it is late on a Friday. I am failing at this explanation. There we go. I wanted blue, why did they give me black? There we go. Blue, please. There we go. There we go. That guy, that component in that little right triangle there, that's the guy that's going to get through. Okay. So if this analyzer is at this angle theta right here, okay, what we can find is that the intensity coming through is going to be equal to the original intensity times cosine of theta. All right. There we go. And actually, hold on a second. I take that back, just really quickly. Okay. What we actually see here, excuse me, the amplitude of that part of the wave, right? The intensity. I'm sorry about that. Is directly proportional to the amplitude squared. There we go. The amplitude of the electric field. So what we see is the intensity is proportional to the electric field times cosine theta squared. There we go. Okay. Since the electric field times cosine theta is the varying electric field right there. All right. And what we see here, if we come over here, is directly proportional to E squared times cos squared theta. All right. And so this, since what we originally said was this right here, and the amplitude, okay, is what we're going to be thinking of as the amplitude of the electric field. Okay, what we end up with is the intensity to be equal to the original intensity times cosine squared theta. Okay, sorry about that first formula. Again, I'm very tired here. All right, so again, the different variables that we have in here, the intensity of the light that passes through is just I, intensity after polarizer, and then I naught is the original intensity. And finally, theta is the angle between the transmission axis and the analyzer. And E is the strength of the electric field. I already said that. Okay. So that's the basic idea right there. All right. That you're going to have some component here of the electric field coming through, and that is directly proportional. That square is directly proportional to the intensity. All right. And that intensity amplitude relationship, this comes from, all right, our work with simple harmonic motion and energy. Remember, intensity is directly proportional to energy. All right? So, whew, quite a lot there, isn't there? Okay, I think I'm going to stop this tape, and then we'll continue on the next one.